Hey there, friends. Today we're diving into the fascinating world of RC circuits. We're going to focus on what happens when a charged capacitor connects to a resistor. So, what are we dealing with here? In this circuit, we have two main players, a resistor and a capacitor. The resistor slows down the flow of electricity, while the capacitor stores that energy like a little battery. Imagine this: our capacitor is fully charged, sitting there with a nice voltage. The moment we connect it to the resistor, something pretty cool starts happening. Here's charging and discharging of capacitor. When you charge a capacitor, it takes a bit of time to fill up, like filling a cup. It reaches about 63% full in one time constant. And when it discharges, well, it drops to around 37% pretty quickly. You can visualize this as a curve. Applications of RC circuits. RC circuits aren't just for nerdy gadgets, they're everywhere. You'll find them in timers, filters, and even audio systems. Here's where it gets interesting. The voltage across the capacitor begins to drop, and it does so in a way that's called exponential decay. It means the voltage falls quickly at first, then more slowly over time. Hey folks, today we're diving into RC circuits, the heart of many electronic devices. Let's find out why they're so important. An RC circuit is simply a resistor, R, and a capacitor, C, connected together. The resistor controls the flow of electric charge, while the capacitor stores and releases it. In an RC circuit, when a capacitor discharges, the voltage across it doesn't drop instantly. Instead, it decreases gradually over time, showing how energy is released smoothly. This voltage drop follows an exponential decay, described by Vt equals V0 E minor C. Here, Vt is the voltage at time t, V0 is the initial voltage, and Rc is the time constant. Check.
Let's say we have a 9-volt battery, a 100 microfarad capacitor, a 10 kiloohm resistor, and a switch which are all in series. The capacitor is fully discharged, and we read 0 volts across the two leads. When we close the switch, the capacitor will charge. The voltage will increase until it is the same level as the battery. The voltage increase is not instant. It will have an exponential curve. At first, the voltage increases rapidly, and then it slows down until it reaches the same voltage level as the battery. We split this curve into 6 segments, but we're only interested in the first 5, because at the 5th marker, we're basically at full voltage, so we can ignore anything past this. Each segment represents something called a time constant. Therefore, as we have 5 segments, we have 5 time constants. So it will take 5 time constants to charge the capacitor from 0 to just under 100%. All we need to do is to calculate how long one time constant is, and then we multiply this by 5. To calculate the time constant, we use this formula. Time constant in seconds equals the resistance in ohms multiplied by the capacity in farads. So we convert our resistor to ohms and our capacitor value to farads, and we see that 10,000 ohms multiplied by 0.0001 farads equals 1. So in this example, the time constant is equal to 1 second. Therefore, 5 of these is 5 seconds. Meaning it takes 5 seconds for the capacitor to fully charge to 9 volts. If the resistor was just 1000 ohms, the time constant would be 0.1 seconds, so it would take 0.5 seconds to reach 9 volts. If the capacitor was 1000 microfarads, it would take 50 seconds in total. Coming back to our original circuit, we can therefore calculate the voltage level at each time constant. At point 1, the voltage is always 63.2%. Point 2 is 86.5%. Point 3 is 95%. Point 4 is 98.2%. And point 5 is 99.3%. So the voltage will never actually reach 100%. That's also why we stop at just 5 points. So in this example, after 1 second, the capacitor voltage is 5.68 volts. After 2 seconds, it's 7.78 volts. After 3 seconds, it's 8.55 volts. After 4 seconds, it's 8.83 volts, and after 5 seconds, it's 8.94 volts. If you needed a more precise answer, we could also calculate each point like this. Remember, because this is in series, the current of the circuit decreases while the voltage of the capacitor increases. Once at full voltage, no current will flow in the circuit. If the resistor was a lamp, it would therefore instantly reach full brightness when the switch was closed, but then becomes dimmer as the capacitor reaches full voltage. When we provide a path for the capacitor to discharge, the electrons will leave the capacitor and the voltage of the capacitor reduces. It doesn't discharge instantly, but follows an exponential curve. We split this curve into 6 segments, but again, we're only interested in the first 5. At point 1, the voltage is always 36.8%. Point 2 will be 13.5%. Point 3 will be 5%. Point 4 will be 1.8%. And point 5 will be 0.7%. For example, if we had a 9-volt battery, a lamp with a resistance of 500 ohms, and a 2000 microfarad capacitor, our time constant would be 500 ohms multiplied by 0.002 farads, which is 1 second. So, at the very moment the battery is disconnected, the capacitor will be at 9 volts. And as it's powering the circuit, the lamp will also experience 9 volts. After one time constant, in this case 1 second, the voltage will be 36.8%, which is 3.312 volts. At 2 seconds, it's 1.215 volts. At 3 seconds, it's 0.45 volts. At 4 seconds, it's 0.162 volts. And at 5 seconds, it's 0.063 volts. So the lamp will be illuminated for just under 3 seconds. Obviously, this will become dimmer towards the end of the 3 seconds. Okay,